Am I audible?
Yes, yes. Good morning. You are audible, but not clearly audible. I mean,
Okay. Um, Let me change my Wi-Fi connection. Yeah, now is it fine? Is it
yes, yes, it is.
better?
Yes, it's better now. It's okay now.
Okay. Okay, so hello and welcome. Welcome to this lecture. Uh, Let me share my screen. So I think today we will sort of break the lecture in two parts. Uh, yeah, I mean, I think we can complete the whole diffusion models part today. So let's try to do that. Let me just recap what we did last time. Uh, okay, okay. Great. So last time actually, uh, we didn't do a lot. What we saw was the basics of diffusion model, right? Particularly, I hope this is recording. Yeah, it is recording. So particularly, what we saw was that okay, how can we convert so what are the restrictions or what are the assumptions that you need to make uh, uh, on top of a hierarchical VAE so as to obtain a diffusion model, right? So these were the three assumptions that we saw. First one just said that well the dimension of the latent vector is same as the dimension of the data point itself, data set the data dimension itself. Uh, I mean, it's quite easy to understand because I mean you are just noising and denoising your data point, so doesn't make sense to have a different dimension for your latent vectors, right? And the other second assumption that we saw was well that uh, the encoder is not learned. Okay, it's a stochastic encoder, but it is not learned. Instead, it is predefined using this linear Gaussian module, right? Where xt is distributed as a Gaussian is distributed according to a Gaussian distribution, which is centered around xt minus one, a scaled version of xt minus one, and with some variance sigma square. And the third assumption was well that the parameters, these parameters, mean and variance parameters A and sigma, these are chosen such that uh, at the end of the forward process, right? At the end of forward process, the final latent vector x capital T is distributed according to Gaussian 0, 1. Okay. And so So these were the three assumptions. And then we sort of saw that, okay, what is the encoder? So we said that the encoder is not learned, instead it's predefined, and it is predefined using this Gaussian map, right? And this was particularly that Gaussian map, right? And using this Gaussian map, we sort of saw that, well, you can write xt in terms of xt minus 1, which is what is defined through this kernel, this transition kernel. However, you can recursively solve it to eventually write xt in terms of x naught directly. So once you know x naught, you can sort of sample any xt for you can if you know x naught, you can sample xt for any t. Okay, and that was an interesting result. And then we also saw that well, if that is the case, what should be the behavior of these parameters alpha t, right? We compared it to what we desire, and we sort of saw that, well, what kind of function alpha of t should be, so that the third assumption that we uh, put, right? The third restriction that we put. can be satisfied. And then we shifted our focus to the ultimate thing, which is the loss objective. This was the loss objective. And the particular term of our interest is this third term. However, this third term requires you to know this distribution, this q xt minus 1 given xt comma x naught. And this distribution is yet unknown to us. We know what is this distribution q of xt given x naught. We also know what is q of xt given xt minus 1. However, we don't know what is q of xt minus 1 given xt comma x naught, right? So what we did then was we did a lot of calculation. I mean, the calculations were not really tough. The calculations were more of, tricks and sort of you can call it as uh, like smart calculation where you just bother with terms that are required and arrange them so that it comes out to be in a nice form. And ultimately what we saw was, well, that your this distribution q of xt minus 1 given xt comma x naught, this is also a Gaussian distribution with a mean and a variance, right? And this is where we stopped, right? So let's go ahead and uh, continue with this, right? So this is 10th, and this is second part of diffusion model, right? Mm, I don't know what is happening with this thing. Just a second. Maybe I should restart. That might help. Okay, yeah. Okay, so okay. So perhaps what I should do is I should again like this is number 10, right? This is it 10. This is again diffusion models. Diffusion models. This is like part 2 of it. Okay. In this lecture, we will particularly see what is the loss function that we use to learn the diffusion model, right? So maybe what I should do perhaps is um, so okay, so maybe I should write down this term that is there uh, in our loss function, this dkl, right? So this KL term, maybe I should write it down. Let me write it down. So this is the term that we are interested in particularly, which is dkl between q of xt minus 1 given xt comma x naught and p theta of xt minus 1 given xt. This is what we are interested in, and we have seen that q of xt minus 1 given xt comma x naught, this is a Gaussian distribution of xt minus 1 with some mean parameter mu q, right? Uh, the final thing that we derived last time is mu q of xt comma x naught and sigma sigma q of t. We have seen this, where what is this mu mean? The mu q of xt comma x naught, this thing is what? This thing is this weird looking thing. Let me write it down. Okay, so yeah, let me write it down. So this term is nothing but this is square root of alpha t 1 minus alpha t minus 1 bar xt plus square root of alpha t minus 1 bar 1 minus alpha t x naught whole thing divided by 1 minus alpha t bar. This is what the mean parameter is. And then there is this variance parameter, sigma q of t. What is this? This thing is also something simple. What is this thing? 1 minus alpha t, 1 minus alpha t minus 1 bar, 1 minus alpha t, 1 minus alpha t minus 1 bar divided by 1 minus alpha t bar. Yes, t bar I. Okay, this is what it is. Okay, now the scale divergence. So let's now think about this term. So we want to learn theta, right? This is what we want to learn. Now we want that p theta is as close to minimizing the scale divergence term, right? Is basically saying that make p theta of xt minus 1 given xt as close as possible to q of xt minus 1 given xt comma x naught, isn't it? So if we are able to bring this distribution close to this distribution, then we are done. I mean, that is uh that is what we want end of the day, right? So to make that thing happen, what we can do, so okay, we want to bring p theta as close as possible to this q distribution. Uh, Now we know that this distribution is a Gaussian, and we want p theta to be as close to q distribution as possible, right? So a natural thing to do is, well, you assume that p theta of xt minus 1 given xt is also a Gaussian distribution. So basically, you assume that p theta of xt minus 1 given xt is also a Gaussian distribution at xt minus 1 with some mean parameter mu theta, okay, mu theta of xt, because remember that during inference we don't have, so in q distribution you had xt and x naught, okay. However, in p theta you only have xt, so you cannot use x naught. So here, the whatever the mean parameter you choose, it has to be a function only of xt. And uh, you can also have now, what about, okay, what about the variance of this distribution? So variance is something that is not dependent either on xt minus 1 or x naught. It is just a function of these parameters alpha t and right. I mean, we just need to know this alpha t's to write down the variance. So in a way, variance is something that you can just substitute as it is, right? I mean, you can just take variance to be whatever it is all. So this is something that you already know because there is nothing to predict here, right? Is this making sense?
So then apart from the alpha t,
Yeah.
we would also be requiring the alpha bar t minus 1, and which is the product of
So
so many alphas.
yes, so alphas are predefined, right? I mean, we discussed it last time that alpha is something that we will predefine. I mean, it has to satisfy certain properties that we discussed here, but nonetheless, it is predefined. You can always calculate these terms at any point of time, right?
So I mean, are these hyperparameter kind of a thing or what? I mean, these
Yeah,
alphas.
this so the alphas are so okay. I mean, in literature, they are called as uh, noise schedules. Okay, so I mean, they are not. I mean, yeah, you can call them hyperparameters because it depends on what kind of schedule you are choosing. But Uh, yeah, it is a hyperparameter, but it has to satisfy certain properties that we discussed here last time. Yeah,
Okay,
but
fine.
but nonetheless, once you define it, it's you can always calculate this term, isn't it?
Right, right.
So so okay. I mean, in the sense, so what is the story? The story is that there is a Q distribution and there is this P theta distribution. We want to make them as close as possible. However, we also know that this Q distribution is nothing but a Gaussian distribution with some mean and some variance. So if I want to make P theta close to this Q distribution, a natural thing to do is, well, assume that P theta is also a Gaussian distribution, right? With some mean and some variance. Now, the variance here is the variance of Q is something which is fixed. I mean, there is not so I mean, but this only depends on these parameters alpha t's, right? So, and alpha t's is something that we already know because we have defined it. We know what sigma, what is this noise schedule, right? So instead of doing something like learning the variance, what we can do is, well, we can fix the variance as it is, right? I mean, we need not worry about the variance of p theta. We can just keep it same as what was the variance of the skew distribution. And the only thing that we need to worry about is this mean parameter. This is the big story. I mean, till now, yeah.
Yes, so even if we assume that this Q is known, or I mean by fixing these alphas, but then
Mhm.
P distribution need to be learned. So,
Yes.
uh, so I mean, if a neural network is learning, I mean these parameters,
Mhm. Mhm.
uh, then how this learning process works?
So okay, I mean p theta is okay. I mean it is parameterized using this uh, parameter theta. What we are doing here is that we know that Q is a Gaussian distribution, and we wa want to say that we want to make sure that this p theta distribution, whatever it is, right, is close to this Gaussian distribution. So since we have this prior knowledge that Q is a Gaussian, we are just simply assuming that p theta is also a Gaussian distribution. Now, where is the parameter coming? The parameter is coming in this mean term, mu theta. Whereas the sigma q is something that we are fixing because we already know what it is. Does that make sense? I mean, it's like saying that okay, there is uh, so so it's like saying that p theta is a Gaussian distribution, but the mean of the Gaussian distribution is something which is learnable. So we are not learning the whole Gaussian distribution. Instead, we are learning the parameters of the Gaussian distribution. Does that make sense?
Yes, yes, yes. But yes, so I mean, how is I mean how is this happening in this way that we are learning the mean of the distribution, but then not learning the
Right.
variance?
So I mean, it's quite simple. So you will have a neural network that will take xt as input and output this mu theta of xt, right? So that will give you the mean. Sigma q is something that you already know because you know alpha t's and everything, right?
Oh, I
So
see.
now, so you know the mean, you know the variance. You just need to sample from this distribution. You employ the reparameterization trick, right? You can do this mu theta of xt plus sigma q half epsilon, where epsilon is sampled from normal 0, 1, right? This thing will be your xt minus 1, simply. The, is
Yes,
it clear?
yes, yes, yes. Right,
So, so, so we are not learning the whole distribution. Instead, we are learning the parameter of the distribution.
right, right.
Okay, so now we have a KL divergence term between one Gaussian and another Gaussian, right? Because Q is already a Gaussian and P theta, we assumed it to be Gaussian. So what is the KL divergence between two Gaussian distributions? That's the question now, right? So I will state this result directly. So, I mean, this is something again that I feel that uh, I should not derive. Instead, we can just simply, use the direct result instead of deriving the whole thing, as we discussed yesterday. So here is this is a standard result rather. So you can just search for it on Google and you will get it. So this is DKL between a Gaussian with mean mu x comma and variance sigma x and another Gaussian with mean mu y comma sigma y. Okay, this this divergence is equal to half half log of mod of sigma y by mod of sigma x, right? Minus d. By the way, this is in d dimension. So this is in RD. Okay. So mu x is perhaps uh, uh, I mean, let's say that the two random variables x comma y, they belong to Rd. So it's in R, so d-dimensional Euclidean space. So that is what D is. Plus a trace of sigma y inverse sigma x plus uh, plus mu y minus mu x transpose sigma y inverse mu y minus mu x, right? So this is the result. Uh, it might look like a lot of terms here, but think about it. If sigma x and sigma y are same, right? This term will become 1 and log of 1 will be 0, right? This is minus d. If sigma x and sigma y are same, then sigma x inverse sigma y is this is just identity matrix, and trace of an identity matrix, this will be equal to d. Minus d and plus d will get cancelled out, and only term that will remain is the last term. So it might look like there are a lot of terms here, but actually it's simple. It's not that tough. Okay. So uh, so using this result, right? So using this result, we want to do, so what is our objective for the diffusion model, right? So this is we want to do arg min over theta, right? This is dkl between q xt minus 1 given xt comma x naught and p theta of xt minus 1 given xt, right? This is what we want end of the day, okay? And so this is equal to what? This is equal to your argmin over theta dkl between, so qxt minus 1 is a Gaussian of xt minus 1 with mean mu q and variance sigma q of t, right? This is the q distribution. And what is p theta? P theta is again a Gaussian that we have assumed xt minus 1 with mean, which is mu theta, and variance, which is same as sigma q. Is this fine? I mean, I have just written what we have discussed till now, just writing it very explicitly,
Yes, yes.
right? So now this is equal to arg min over theta. Now we know what is the KL divergence between two Gaussians. This is the result, right? So we will just use that. So this is half. So this was log of determinant of sigma q of t divided by determinant of sigma q of t, right? Minus d plus trace of sigma q of t inverse sigma q of t, right? Because I mean both the variants are same here, right? That is what I was saying, that it might look difficult, but it becomes very simple. Plus mu theta minus mu q in transpose sigma q of t inverse mu theta minus mu q. This is what it is, right? So now this thing becomes zero. Maybe use another color. This thing becomes zero. This thing actually becomes equal to D because this thing is equal to I, right? And trace of an identity matrix is just the number of diagonal elements that it has. So this is a D-dimensional space. So the variance has a D cross D, this thing, D cross D variance or covariance matrix. And hence the sum will be D, and minus D and plus D will get cancelled out. So all that we remain with is this is argmin over theta of uh half mu theta minus mu q transpose sigma q of t inverse mu theta minus mu q. This is what the loss function finally is. Now what is sigma q of t? sigma q of t. We saw what this was, right? Yeah, this is what sigma q of t is. This is 1 minus alpha t, 1 minus alpha t minus 1 bar divided by 1 minus alpha t bar, right? So this is 1 minus alpha t, 1 minus alpha t minus 1 bar divided by 1 minus alpha t bar I. This is what sigma q this thing is, right? So what will be what will be its inverse? So the inverse, this the sigma q of t inverse, this will be nothing but, I mean, these are just, so this is a diagonal matrix, right? And the diagonal, all the diagonal elements are same. So the you can just inverse the scalar outside and the identity matrix will remain as it is. So this will become 1 minus alpha t bar divided by 1 minus alpha t, 1 minus alpha t minus 1 bar I. Okay. Uh, so this is actually, this is nothing. So if you call this, so if you call this thing as equal to sigma q, small sigma q square, this is equal to 1 by sigma q square I, right? Nothing fancy. So substituting it back into our objective, maybe what I can do is I can change the color here so that it comes that this is a side calculation. Make it this thing. Uh, yeah. So what the argmin will become? So this argmin over theta half. So this is mu theta minus mu q transpose uh, 1 by sigma q square I into mu theta minus mu q, right? This is what it will become. And you can take this thing outside. So this will simply become arg main over theta 1 by 2 sigma q square mu, and so this thing inside will become mu theta minus mu q norm L2 norm whole square. This is what it will become, right? So x transpose x is norm of x. That is what. So x transpose x is norm of x square. That is what I have used here. Uh, to be very explicit, let me write this thing again. So this is arg min of theta 1 by 2 sigma q square norm of, this is mu theta, which is function of only xt, and mu q, which is function of xt and x naught, this square, right? So this is what the loss function is. So basically, your if you want to learn this mu theta, so if you want, so to to denoise, right? So in the reverse process, when you want to generate new sample, all you need to learn is first of all this mean parameter mu theta. And what is that mean parameter? The mean parameter is just telling you that this thing should be equal to this mu q. However, the problem here is that while calculating mu theta, you only have access to xt, whereas mu q here has access to both xt and x naught. You don't have access to x naught here. I mean, if you had access to x naught, there is no point of generation because you already know what is the denoised input, right? I mean, what is the denoised output? So, so, so yeah, this is finally the loss function. So the loss function is essentially just telling you that to learn theta, just make sure that the mean of this mu theta, so the mean of your p theta, which is mu theta, is equal to the mean of q function, q distribution that we saw. This is mu q. If these two are same, then you have learned your theta basically. Okay.
Yes. And what this sigma q here is, I mean, how did we represent this sigma q?
Sigma q is the scalar that was outside. Sigma q, remember, sigma q is this thing. This thing. I
Yes.
mean, this whatever. So this is sigma q. This is also a function of time. This is 1 minus alpha t, 1 minus alpha t minus 1 bar divided by 1 minus alpha t bar. This is what it is.
Yes.
So you would know this thing because you know what alphas are, right? Right. Okay. So we have come till here, right? Now let us see. So let us see if we can further simplify this thing, this term, right? Let us look at it. So you know what mu q of x t comma x naught is, right? We know what this is. What this is, we have derived it earlier. This is so this thing, right? So this thing. This is what this mu q is. So let us write it down. So mu q is what? Square root of alpha t, 1 minus alpha t minus 1 bar xt, okay, plus square root of alpha t minus 1 bar 1 minus alpha t x naught, right? Divided by 1 minus alpha t bar. This is what our mu q is. We want to make sure that mu theta of xt is as close to mu q as possible because that is what our loss function wants, right? Now, but however, what is the problem? The problem is we only have access to xt. Mu q also has access to xt, but it also has access to x naught. Particularly, if I want to write mu theta, I can write this term, I can write this term, but I cannot write this term. I mean, I cannot write this term. Why? Because I don't know what x naught is, isn't it? Does that make sense? That if I want to directly write mu theta, I mean, if I want to reduce this loss function, right? I can if I know what mu q is, I can this loss will become zero because mu q minus mu q will be zero, right? However, if I try to write mu theta as like equal to mu q, the what is the problem? The problem is that I won't be able to calculate the second term, isn't it?
Yes,
Because
yes.
x naught is unknown to me. So what I can do instead is I can take mu theta to have this form where I the first term everything is same, okay? Xt plus something derived divided by 1 minus alpha t bar, okay? However, what I will do is what is unknown to me? This is unknown to me, right? I mean, particularly this x naught is unknown to me, isn't it? If I
Yes.
what I can do is I can simply say that, well, my mu theta is of this form where I have this thing, because these are constant, I already know that. And I can make this thing as x instead of no x naught, I can make it x theta hat of xt comma t. So what I have done here is, see, I wanted this mu q to, if I knew exactly what this mu q is, like this term is, my problem is solved. I mean, I don't need to do anything. I can simply use this thing. However, the problem is I don't know x naught, and that is what is causing me trouble. So what I can do instead is, well, I know what is the form of mu q. Mu q has this term, and this term. Out of these term, this is the term that I don't know. So what I can do is I can say that, okay, mu theta, my mu theta will also have this exact same form. However, what is unknown to me will be so this thing is unknown to me. Particularly x naught is unknown to me. So x naught is something that will be learned by my neural network. So my neural network will take xt and t as input. It will predict some x theta hat. And once I have x theta hat, my mu theta will take this form. And my mu q has this form. Is it making sense or is it weird?
No, it's true. But then, since
Mm,
since the denominators are same, so to keep the numerator same, is
mhm.
it necessary that these alphas would remain the same for the mu q and as well as for the mu theta? Because we want both the values to be same, so quite possible that for the mu theta, the values of the
Mhm.
alphas may differ.
I mean, it is possible, but that would complicate things, right? I mean, like it would. So it's like I know so alphas are something that I need not worry about because these are something that I already know, right? I mean, alphas are something that I already know.
So
So
alphas,
I can make my form of mu theta as tight as possible by keeping everything same, but only changing something that I don't know.
I see. So since we know the values of the alphas for q, and so how would this theta would come to know about this these alphas? I mean,
It
how
need
the
not. It need not know. It need not know. So you see, x theta is only taking xt and t as input. It is not taking alphas as input. So
uh, alphas as input, but then to make the things equal, I mean, in the
mhm,
numerator, it is also, I mean, having the
yeah.
information of
Okay,
the.
I think it will become more clear if we simplify it further.
Okay,
Let's
okay.
do that. So let's do that. So till now we have reached till here, right? This is our loss function till now. Let me write it down. So the loss function objective. So the whatever loss is, this is arg min. So theta star is arg min over theta of 1 by 2 sigma q square norm of mu theta uh, minus mu q whole square, right? This is what our loss function is. Now, if you assume that mu theta and mu q have this form, right? This form. And if I substitute it in my loss function, what it will become? This will become arg min over theta, right? This will be 1 by 2 sigma q square. What will be inside? So mu theta has this form now. It has this form now, right? This thing. So let us write it down. So this is square root of alpha t 1 minus alpha t minus 1 bar, right? Xt plus square root of alpha t minus 1 bar 1 minus alpha t x theta hat, okay, divided by 1 minus alpha t bar. This is my mu theta. There's a norm outside. This is mu theta. And what is my mu q? Mu q is nothing but alpha t 1 minus alpha t minus 1 bar xt plus square root of alpha t minus 1 bar 1 minus 1 minus alpha t. We have x naught here directly. That's the only difference. So 1 minus alpha t bar. This whole norm square. This is my final thing, isn't it? Now you can see that a lot of things will cancel out, right? Particularly this thing and this thing will get cancelled out because they are exactly the same. That is the beauty of doing this parameterization. That is the benefit of assuming that mu theta has this exactly this form except something that is unknown, that is x naught. That what is
Yes,
redundant will get cancelled out.
yes, yes.
Okay. Now, uh, what remains? So this is arg min over theta 1 by 2 sigma q square, right? What is remaining? So this is square root of alpha t minus 1 bar, right? To 1 minus alpha t divided by 1 minus alpha t bar, right? This is what is remaining into x hat theta of xt comma t minus x naught, right? So maybe this since everything else is scalar, that will come out. Uh, maybe let it be x hat x naught, right? The norm of this whole square, right? This is what it is. What we can do is we can take this term outside. This will become arg min over theta. Uh, if you take this outside, you have to square it. So this will become alpha t minus 1 bar, right? Uh, 1 minus alpha t square divided by 2 sigma q square 1 minus alpha t bar square. And inside you have a norm of x hat theta of xt comma t minus x naught whole square. So finally, the objective, the optimization of diffusion model boils down to learning a neural network, right? This neural network which predicts the denoised input X naught. So basically, what is this thing doing? This is so this 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 objective is telling us, well, I give you a noisy input xt and the corresponding time t. I feed it to a neural network. The neural network has to basically predict the denoised input x naught directly. This is what the learning of neural network boils down to. Once I have, so after I learn this network, after I learn this uh, network x theta, what I can do is I can substitute it here and calculate mu theta. Once I have mu theta, I can simply then if I if I calculate mu theta, I have this distribution, right? P theta of xt minus 1 given xt because I know the mean, I know the variance. So I can sample xt minus. So right now I'm at xt. I can sample xt minus 1 if I know what this Gaussian distribution is. Is this clear or is it making sense?
Yes, this is making sense.
So what will we do during inference? Just to be very clear, right? So this is inference. Inference meaning inference or while generation. What are we going to do? So we have theta star. Okay, we have this theta star. Okay, this means that we know what this p theta star of xt minus 1 given xt is, isn't it? So what are we going to do? We are going to start from some x capital T. This is sampled from some Gaussian 0, 1. Okay. Now at each t, what we are going to do is we are going to calculate x naught hat, which is going to be this x theta hat of xt comma t. Okay. I mean, this is our neural network x theta star rather. So we have learned the neural network, right? So I will pass my xt and t to the neural network and I will get this x naught hat. From this x naught hat, I will calculate mu theta of xt, right? Which has that form, whatever form. Once I have that form, what I will do is, so basically I know what this p theta of xt minus 1 given xt is. This is a Gaussian with mean mu theta of xt, comma sigma q of t. Right? I know this. So what I can do is I can do xt minus 1, which is equal to mu theta of xt plus sigma q of t half epsilon, where epsilon is sampled from Gaussian 0, 1. This way I have obtained xt minus 1. From xt minus 1, I will again repeat this process. I will get xt minus 2. So I am going to start from this xt. I am going to calculate x capital T minus 1 from here, so on so forth until I reach x naught. So I started from a Gaussian noise, okay, and I have come to a data point x naught. This is how, when I have to generate a new data point, this is how I am going to sample, uh, generate my data, right? And how am I going to learn this theta? So the theta, okay, another thing that I mean, a small point that I sort of just bypassed through is that, well, there was a summation over the scale terms, right? If you remember, yeah, there was this summation. So this was the elbow and we were maximizing it. So we have to minimize this term. Minimizing this term is okay. I mean, you have to sample from this expect q of xt given x naught, but there was also this summation. To avoid that summation, what we do is so the objective to learn theta. Uh, that so what we can do is we can instead do argmin of theta. So instead of doing it, so there was a summation over all time steps here, right? This was a summation over all time. Instead of doing that, what we can do is we can sample some random time instances from a uniform distribution between 2 and t, right? Like randomly sample time steps. That's all. There is a uniform distribution over all the time steps. You just randomly sample a time step. For that time step, you calculate q of, you get a xt. using this distribution q of xt given x naught, and uh, minimize the scale decale between q of xt minus 1 given xt comma x naught and p theta of xt minus 1 given xt. Okay. This is, and this thing we just saw is equal to nothing but what? This whole term, whatever there is some constant term and norm of x theta hat of xt comma t minus x naught norm square. This is the learning objective, and once you have learned it, this is how you are going to sample from the diffusion model. Is this fine? Any doubts here?
Yes, I could understand this, except this portion wherein you wrote that this p theta, this xt minus 1 is equal to mu theta xt plus this entire thing.
Mm-hmm.
So my point is that from xt, the target is to reach to the x naught and not to any intermediate point in between. Is it so?
No, no, no. So that was the case with the forward process. So in the forward process, we had this thing that at from like in the forward process, right? While going in this direction, you could reach directly from x naught to x capital T. That is how the kernels were. However,
Yes.
while going backward, I cannot reach directly from xt to x naught. Instead, I have to like sequentially denoise it. I have to go
Yes.
through all the steps because I don't know what is p theta of x naught given xt. All I have learned is p theta of xt minus 1 given xt. This is what I have learned.
Yes. Yes. Now I understood. Yeah. Fine.
Yeah. Right. So this is so I mean, if you know this much about diffusion models, I think you are like good to like at least like do some basic stuff with diffusion models. This is because essentially this is what it is. What I will do is I will like take a break here and I will cover one more thing that is quite interesting, which is what if you want to learn the these parameters. So till now I know that I haven't been very, so I have given intuitions about what these alpha t's should be, but what if you want to learn the alpha t's as well? Like if I want to basically make these alpha t's learnable as well, can I do that? That's the question. And that is something which is interesting. And I will take a break here and I will come like complete that. Okay. So let me stop the recording and restart it.
Yes.